In this video, I would like to talk about the solution of discrete time state space equation. Okay, let's start with the fact that, or the case that u of k is equal to 0, so there's no input, and x of 0 is equal to some initial condition x naught. Okay, so in this case, we can write xk plus 1 is equal to j times x of k, whereas y of k is equal to c times x of k. Of course, we can have the u of k, but input is equal to 0, so we don't need to do that, so it's just that. Okay, so let's start writing computing the x1, x2, and try to figure out the general format. Okay, so x1 is equal to g times x naught. Okay, of course. x2 is equal to g times x1, and it's equal to, as you can see, g square x naught. Okay, similarly, x of 3 will be equal to g cube x naught. This is cube. And x of k is equal to g to the power of k x0. Similarly, y of k will be equal to c times g to the power of k x naught. As you can see, computing initial condition response is very easy. Okay, so finding a analytical closed form expression of g of k may be tricky, but it's kind of still doable. And as you can see, the solution of a discrete time state space equation, zero initial condition case, is much easier compared to solution of a general continuous time state space equation. Okay, it's also very easy to see that x of k is equal to, okay, so if we start from arbitrary initial time, x of p, g to the power x minus p. Okay, so in the solution of linear time variant systems, g of k in the contents context is called state transition matrix of the system, okay, times x naught. Okay, no, that's just this, okay. And state transition matrix is technically the mapping of a state in time to a different state in time. It is like g to the power of k for discrete time systems. It is similar to the e to the power of t in continuous time systems. Okay, so one of the important features, interesting features of the state transition matrix is that if you put state transition matrix into the homogeneous equation, no input, you'll see that it can solve the equation. So the matrix can technically solve your discrete time state space equation under the case that input is equal to 0. So it's more powerful than you think, and it's technically similar to the e to the power lambda t in differential equations, or a to the power k in differential equations. It's the basis or the fundamental function that can solve your technically difference or equation or state space equation. Very good. Okay, that's nice. Okay, so let's now analyze the case. Okay, x naught is equal to 0, no input, but we have no initial condition, but we have input. Okay, g to the power g times x of k plus h times u of k. Let's analyze the output separately. Okay, x of 1. Okay, so we have input but no initial condition is equal to h times u 0. That's great. X of 2 will be equal to g times x1 plus h times u1, and g times x1 is equal to g times h times u0, so it is equal to g h u0 times h u1. Okay, if we compute x of 3, we will see that it will be equal to g to the power 2 h u0, and now we are obtaining a pattern g times h u1 plus 0 1, okay, h u3. Okay, so the index of u is increasing in this direction wherever index of g to power is increasing in this direction. There's like a convolution operation. Okay, so as you remember, in the convolution we have like impulse response, which takes the argument n to the power minus k, and u takes the n to k. So there's some like a convolution, indexing in here. It's convolution. I will show you later. Okay, good. So for a general x of k, so I can find this relation. You will see that it starts with g to the power x minus 1. Okay, h times u0. Okay, that's nice. Plus g to the power x minus 2, h times u1. It goes like this. Okay, so last two elements, g h u k minus 1 plus h times u k minus k minus 2. This should be k minus 2. Okay, that's great. And this should be k minus 1. That's great. Okay, so this is the relation. So as you can see, we have a summation. We have inputs that we control. Okay, so these are the user applicable control inputs, and G's and H's are like system matrices. They're like coefficients, the powers. So what we can do is we can write this in a compact matrix form like this. Okay, we have a weight matrix k minus 2h. This is the first element. G to power k minus 2h. It goes like this, gh, and this is h. That's great. So this is a known matrix. This belongs to the system. And here we have u0, u1. It goes like this, u k minus 2, u k minus 1. I really like this equation. Okay, so this is for a single input system, n-dimensional vector, which technically stores all of the inputs that we can apply to the system. Okay, and these are the weighting variables, matrices, vectors, whatever you say, which technically takes each input, maps to the output. And obviously, state output at time k is a function of the inputs and also a function of the system parameters. Okay, that's great. And I will use this derivation when talking about reachability and control of the system. Okay, I can also write this in a technically summation form. J is equal to 0 to k minus 1, g to the power k minus 1 minus j. Let's write it like this. H times u of j. Okay, similarly, if I just change the order, I can write this like this. N is equal to 0 to k minus 1, g to the power n, h u times k minus 1 minus j. As you can see, this is not exactly a convolution, but it looks like a discrete time convolution. Okay, so if you make some necessary changes of variables, you will see that this is actually the convolution operation. Okay, good. So that's nice. So similarly, if I replace g of k with phi of k state transition matrix, I can also rewrite the equation, which looks like this. Okay, it is equal to j is equal to 0 to k minus 1 state transition matrix j multiplied with h times u. Okay, k minus j minus n, and something like that. Okay, so this is the response of the system for input we already covered initial condition. Since these systems are linear, we can easily combine them. Okay, so if you want to compute y of k, which is very easy, I simply multiply the states with c and add d times u of k. Let's use this formula. Okay, it's equal to n is equal to 0 to k minus 1 c times g to the power n times h. Okay, that's great. U times k minus 1 minus j, of course, plus in just the other part d times u of k. Okay, so we find the solutions. Okay, so it may be complicated. Okay, so but actually it's not. If you know c, if you know g, okay, if you compute g to the power k and h, it's kind of relatively easy to do that. Okay, but in general, if you want to compute, for example, time domain solution for a limited number of k, let's say from k to 5, doing like the forward equations like this may be the easiest way to do that. Okay, just compute x1, x2, x2, and can go like that. Okay, this is more like a general solution, and we generally use these derivations to talk about the controller reachability, controller design, and other techniques. Okay, nice. That's good. Now let's talk about z-domain solution of state space equations. Okay, so technically we already covered one part where we compute the transfer function y of c is equal to c times zi minus g inverse, okay, h plus d, that's great, times u of c. Okay, that was nice. Okay, we already computed that. Okay, so in this case we can also take the inverse Laplace and find the, for example, if you take the inverse Laplace test, it will be the impulse response of the system. Now let's try to analyze initial condition response, where u of k is equal to 0, but x of 0 is equal to x naught. Okay, and so in that respect, we can write the equation as this: x plus 1 is equal to g times x of k. That's it. So if we take the inverse Laplace, we can say that it is equal to z times x of z. But since we have initial condition, this is minus z times x naught is equal to g times x of z. Okay, so if we reorganize, we can see that zi minus g x of z is equal to that. What's that? Okay, that's great. See x0, there is some mistake in the lecture notes. I will correct that. This is x0. So x of z, okay, so this is z, right? Okay, this is z, is equal to z times, okay, zi minus g inverse times x naught. So we already computed the x of z. Similarly, we can compute y of z as equal to z times, we here, c times zi minus g inverse x naught. As you can see, it's fairly easy to do that. Okay, so one important thing is, okay, so let's concentrate on this part, clean that. Okay, that's good. So if I take the inverse Laplace of this, what I will obtain that x of k is equal to, not inverse Laplace, inverse z transform. So for that, okay, z to the power minus 1, okay, okay, so clean that. Let's make it nice. Zi minus g inverse times x naught. Okay, so what is this? Okay, this is equal to g to the power k, which is equal to state transition matrix of k, and it is equal to inverse z transform of z times zi minus g inverse. So if your goal is to find a closed form expression of state transition matrix, okay, instead of doing the fourth equation, this technique may be a better way of computing that. Okay, yeah, just like take the zi minus g, take the inverse, multiply it with z, take the inverse z transform, which will give you a closed form or analytic expression for g to the power k. Okay, good. That's nice. So let's look at it. It's nice. You don't need to do that. Okay, so now let's try to solve some examples and try to figure out how we can use these derivations techniques to solve examples. Okay, that's nice. Okay, so we have x of k plus 1, which is equal to 1, 0, 0, 0, 1 over 2, 0. That's good. 0, 0, minus 1, which means that we have a diagonal contour representation, which should be good because of ease of linear algebra mathematics. 1, 1, 1, u of k. Okay, and we have y of k. Let's write it here. Y of k is equal to 1, 2, 3, x of k. We don't have anything. Okay, so the first question is compute the closed form expression of state transition matrix. So we need to compute phi of k, which is easy because phi of k is equal to g to the power of k, since it's in diagonal canonical form, okay, which is equal to this matrix power to the power k. So in diagonal canonical form, if you just take the power of an element, you just simply take the power of each diagonal, so it's equal to 1, it's not changed, 0, 0, 0, 1 over 2 to the power k, 0, 0, 0, minus 1 to the power k. As you can see, it's very easy. We don't need to do any complicated derivations. Okay, good. So the second question is compute this using the z transform method. Okay, let's do that. Okay, so let's clean this. Okay, so it will be also relatively, it should be relatively easy. Okay, so okay, clean that. So what we need to do is we need to compute zi minus g inverse first, and then take the inverse z transform. So this is equal to z, okay, zi minus g is equal to, so z minus 1, 0, 0, 0, z minus 1 over 2, 0, 0, 0, z plus 1. I think it should be correct. Let's check it. Should be correct. Okay, that's good. Okay, take the inverse. Okay, taking the inverse of the diagonal matrix is super easy. It's equal to z, okay, 1 over z minus 1, 0, 0, 0, 1 over z minus 1 over 2, 0, 0, 0 over z plus 1. That's great. So I add z here. Okay, so let's put it here. Okay, let's clean the ones. Okay, so if you look at the tables, you will see that like inverse of this is equal to, okay, 1, 0, 0, because step input. Okay, 0, 1 over 2 to the power k, 0, 0, 0, minus 1 to the power k. So we compute the same result. Of course, we assume that k is greater than or equal to 0 because this is the state transition matrix. So it's mapping 0 to other states. Okay, good. So what we can do that? Okay, compute impulse response of the system from the time domain solution. Okay, that's good. I think we can easily do that. Okay, so in order to do that, let's look at one of our derivations. That's great. Okay, so we are computing the impulse response of the system. Okay, that's great. So, okay, so what is impulse? Impulse is u of k. So let's clean that. U of k is equal to sigma k, and this is equal to 1 at k is equal to 0. Otherwise, k is equal to it is equal to 1 when k is equal to 0. Otherwise, it is always equal to 0. So x, let's compute x of k. Okay, let's clean that. So u0 is 0, u0 is 1, and any other thing is equal to 0. So I will simply clean every other thing to have some space. Okay, that's good. So we already computed that. That's great. This is u0. u0 is equal to 1. Okay, that's good. So if I compute y of k, because it's the impulse response, I need to go to multiply with the c. Okay, c g to the power k minus 1 times h, and this is only true, of course, when k is greater than 0, because it's the impulse response of the system. Okay, that's great. So how we can compute that? It's equal to, what is c, if you remember? C is equal to 1, 2, 3. Okay, so I need to multiply g to the power k minus 1. I already know that. It is 1, 0, 0, 0, 1 to the power k. Okay, so it is not nice. 1 to the power 2 k minus 1. This is 0, 0, 0, minus 1 to the power k minus 1. That's great. And of course, I need to multiply with 1s. Okay, that's great. So if I compute it, y of k, or technically it's equal to g of k, impulse response of the system, is equal to 1 plus 2 times, okay, 1 over 2 to the power k minus 1 plus 3 times minus 1 to the power k minus 1. And of course, this is equal to true only when k is larger than 0. Okay, so what is next? It says that compute the transfer function. Okay, that's great. We can do that. So let's have a space. Okay, so what is transfer function? We don't have z, right? No, we don't have d. So t of z is equal to c zi, okay, z times I minus g inverse times h. Okay, so it's equal to 1, 2, 3. I already computed zi minus g inverse. Okay, it was equal to 1 over z minus 1, 0, 0, 0, 1 over z minus 1 over 2, 0, 0, 0, 1 over z plus 1. That's great. Times, okay, 1, 1, 1. That's good. If I just computed that, I will easily see that it's equal to 1 over z minus 1 plus 2 over z minus 1 over 2 and plus 3 over z plus 1. Okay, that's great. So do we have anything left? Okay, compute the inverse z transform of the transfer function. Okay, very good, which will give you the impulse response representation. If you take the inverse z transform of this, you will see that it will be equal to t to the power of k, okay, 1 plus 2, okay, 1 over 2 to the power k minus 1 plus 3 minus 1 k minus 1, but multiply with h minus 1. Okay, so k minus 1. Okay, you can look at the lecture notes for the other day. So it's the same thing, but this is equal to true for k is greater than or equal to 0, because it also includes the 0 because of the impulse case. So if you remember, I told that this is this. Okay, this is true for k is larger than 0, and impulse G0 is definitely equal to 0 because we know that initial condition equal to 0, and if we add the impulse, it affects other things because we don't have any D matrix. Okay, that's great. Okay, as you can see, we computed many other things like impulse response, transfer function, like transition matrix. Okay, they are of course useful because when analyzing the system behavior for like specific input, impulse response, to talk about stability, we need to able to use this kind of tools both in computational and analytical form.